Our next presentation is from Nonspec. They're from the University of Massachusetts in Lowell, and they've been working with Total Plastics. I do believe they're very happy to be down here in South Beach this week, and if you welcome them to the stage, we'll find out about their design and application.
Quite a few people. Waiting on a mic.
Okay.
There we go.
Good afternoon, everyone. Today we would like to introduce you to a product that has the potential to change lives. Every year, over 1 million cases of amputation due to infection, injury, and disease are reported. Roughly 1/3 of these amputations are upper body amputations, ranging from a fingertip to the entire arm. In nations such as our own, patients have easy access to healthcare and insurance when choosing their prosthetics. Indeed, in the United States alone, the purchase of prosthetics is over a $20 billion a year industry. We have come to expect a prosthetic hand that models a real hand, with motorized joints, some myoelectric functionality, and we expect these features in a customized design fitted to the individual amputation site. However, in developing nations, prosthetics such as these simply are not within the means of normal families, and the additional components can often be more of a burden than a blessing. Motors fail with grit and dust. Electronics need to be replaced and charged, and customization increases the cost by an order of magnitude. This is especially problematic for children amputees, most of whom need to replace their prosthetic about as often as they would outgrow a pair of shoes. The need is so great that in some areas, people have taken to heat-forming soft drink bottles to the amputation site in order to provide a temporary solution. We believe there is a better way. We have prototyped a durable limb that grows with the patient. It is simple to use and adjust and will allow children everywhere to return to a normal lifestyle.
We looked at limbs throughout history, and we found that the earliest units were mostly crude hooks and pegs with non-human-like shapes. This is due to both the complexity of the human form as much as it is the material they are made from. The limitations of cost and quality often made them only available to those who had the means to afford them. For instance, in the Middle Ages, knights who lost limbs often had a prosthetic piece built into their armor to hold a shield or lance. However, for the common person or the impoverished, whose life and work often led to higher rates of amputation due to disease or accident, there was just no way to make the same utility and look of a human arm. Thus, we have hooks which function as needed. Today's prosthetics have evolved greatly from their roots, but the costs still remain so high that the majority of people who would benefit from them can seldomly afford them without adequate health care. To form our design, we studied prosthetics throughout the ages and concluded that our product must be low cost, simple, robust, and yet still mass producible. To start with, this elbow joint works on a gear-like system to lock into a natural range of motion and has an easy-to-use push-to-lock system. The system is resistant to dirt and is simple enough to be used by a child while still maintaining minimal maintenance.
In keeping with this design, one of the things that we tried was to keep the arm as simple to use as possible while still gaining the maximum functionality. And so we actually went back to a bio design and we said, how can we replicate natural human motion, natural human growth? And because our product is targeted at children, the most important thing for us was to ensure that they didn't need to buy 8 prosthetics or 4 prosthetics even for the course of a small period of time, because the cost is absolutely astronomical. And so we have one device which can expand over the course of its use. So right now I have on me the 8-year-old version of this model with a hand attached to it. And then I have the exact same model which has been fully expanded because I fiddle horribly whenever I try and do these on stage. And this is the exact same model, but it has been expanded out to the 16 to 17-year-old range. And the change in length is actually incredibly important because it really decreases the cost overall for the children. And the hand is the other major component on the end of the arm, I suppose. What's really important about this is we went back to fundamentals of engineering and all of our classes that we learned so much about. And we actually went with a linkage design, which can be snapped together really simply. It's really elegant in execution, and it transfers a lot of force very quickly. Our first design was all out of aluminum, and I actually have quite a few of those on hand with me. They were the easiest for us to machine, and we realized that this was not a sustainable solution to give to people in countries who did not have the resources that we had access to. So we redesigned the hand so it could hold the weights that it needed to hold, but not cost so much out of pocket that people couldn't support themselves and buy a hand.
To meet our low cost point of $20, we've decided to injection mold all of our components out of polycarbonate. This will allow us to meet our high demand with only a high overhead. Plastics gives our product a natural feel that meets FDA requirements. Our parts are very small and require high tolerancing, and the molding process allows for a high quality and repeatable process. Our prosthetic is able to replace a limb from the low shoulder down, including individual fingertips. The design has interchangeable parts, so they're easy to replace and customize. We have spent many hours in the machine shop, CNCing, tapping, coring, everything you can think of, and to make our prototypes. Our current prototypes are made out of PEEK and nylon rods provided to us by Total Plastics Life Sciences. We plan to make all of our own molds and have an in-house production in the future. The centers of both the forearm and the upper arm have hollow cavities that can be filled with a weighted object, such as a sealable plastic bag with water and chlorine, that will allow the child to develop naturally balanced muscles and a normal spinal curve. And the skin is still in the works. It will be an elastomer that will cover the skeleton and will be easily pulled down to adjust the size of the prosthetic. It will be a blank template that the patient can customize to their own liking. And it'll be a flexible design that will protect the inner workings from water and normal wear and tear.
Since our design is geared towards children in developing nations, we wanted our prosthetic to be strong and robust, so if the child had to lift objects to help around the house, do chores, or work, they would be able to. So the initial goal was for the hand to be able to lift a 5-gallon bucket of water, which is around 70 pounds and more than what your average child can carry. In reality, though, the design goes above and beyond that. So on the slide here, you can see our arm being used to hold a over 200-pound anvil. And it did a really good job, didn't deform or anything, so I think we met the goal for that. And then we also tried rolling the anvil over to see if we could crush it. It actually held out really well, too, for that. So the next thing we had to consider was how we were going to distribute and fund our device. So currently we're involved in a couple competitions going on and applying for as many grants as we can find. We're also looking for individuals, contacts, and possible investors to help us out. We've also are constructing currently a webpage, www.nonspec.org, and we have profiles on several popular social media sites such as Facebook, LinkedIn, and Twitter. We are, since we wish to distribute our product inexpensively, we have been looking at several charities and NGO models for inspiration. In the end, we decided to create the Give a Hand Foundation. The Give a Hand Foundation is similar in model to Amazon's One Child Per Laptop or Tom's Shoes. It'll be taken care of using public and private sales and donations. We'll be working directly with NGOs and charities to help distribute our vise. Since our vise can be taken apart, it can be actually put inside existing shipments, such as like pockets between water bottles. We also are planning to work directly with the medical care providers. We are creating training videos that can be sent to healthcare providers overseas, and we'll offer training in the US as well. We plan to work directly with the providers so that we can provide the necessary levels of customization and reach the needs of the individual child. Another option that we've been considering is selling our product on the domestic market as a way to support the foundation. Our device has possible uses in the medical field as a sports prosthesis. Now, children here in the US have much more options for health care and can afford expensive prosthetics, but however, the average family cannot afford to destroy a several $1,000 prosthetic during a game of tag football. Our device is very strong and robust, and it's inexpensive, so if you break it while playing during rough activity, first of all, it will be a ductile fracture, so safety is good, and secondly, it won't break the bank to replace it. So another option is using it as a starter prosthetic for children who have just had a procedure for amputation while they wait for their customized prosthetic to be built. It'll get them used to having a prosthetic attached to them, which some studies have shown is good for the child's development. So currently we're working on finishing up the mold, then we'll go into mass production. Based on the injection molding, it'll actually get cheaper for us in the long run to produce. And right now, after we're done with the design, we'll be working with volunteers at a local VA hospital. They'll be testing out our design for a few months, and then based on their feedback, we'll fine-tune the design and then start working with NGOs and other organizations to help distribute our device. So we'd like to get our knowledge out there, and we believe that currently, based on the market, that we'll be able to corner a large portion of the upper extremity prosthetic market based on the design and robust nature of our prosthetic. So we'd like to extend our thanks to all of you for listening to us. We'd also like to thank Total Plastics Life Science Division for providing us with materials from Quadrant and Atlas Fiber. We'd like to thank UMass Lowell for helping us in guidance and support, along with letting us use their equipment facilities. And we'd like to thank the IAPD, Liz Novak, Whitney Nelson, and everyone else involved in this process. Feel free to come up to us afterwards. We'll be hanging around, ask questions, and we look forward to meeting many of you. Again, thank you.
And if there are any questions, yeah, so many of us talking at once. And if there are any questions, please don't hesitate to ask. All right, thank you. Oh, back there, sorry.
I was going to say, we couldn't have covered everything.
Have any material? Hi, Keith Bateman with Westlake Plastics here. You settled on nylon and PEEK, I believe, for the rods. Mm-hmm. Were there any materials that you either failed or you ruled out?
Quite a few, unfortunately. I think a large portion of our time in building the forearm was actually spent trying to choose which plastic to use, and I'm trying to remember which ones we went through right now, but we had not very few plastics passed our wear test, actually. It was the largest problem. And so what we did was we tried to basically over-thread our own rods, so we just kept twisting and twisting and twisting and seeing how it would behave itself. We ended up settling on nylon because it behaved the best with the PEEK rods and, as the threaded rods. Our future design goals is actually to find one plastic which will make up the whole design. And I think we're looking at testing polycarbonate soon. So I don't know if that answers your question exactly, but basically we broke quite a few. I have little plastic pieces all over my garage right now, so it's a good design process skill. And your kitchen table. Any more questions? Yes. Oh, microphone is inbound.
Perhaps you mentioned it and I didn't hear it, but how do you actually adjust the length? Is it telescopic there?
It is telescopic. So the way that this works is that this is basically just a turnbuckle. So this is a left-handed rod and this is a right-handed rod. And so when you turn it, it either tightens or elongates. There was a time when I tried to do this on stage repeatedly and I just ended up sitting there for 5 minutes just trying really hard to make sure everything behaved itself. And so we've stopped that and we just bring two already extended and they come out really nice. The benefit to this is also that smaller children are known for their impacts. They fall down a lot. When we started looking at numbers, kids fall down. We tried getting some hard data on that, on how often little children fell over, and the numbers were insane. And so the turnbuckle actually protects the rods during little spills and trips as the child is developing, which really keeps them from bending as they get older. And then when they get older, you see a lot less really harsh impacts from 5.5 feet tall to the ground, which is a wonderful thing. Yes, so. More questions? Sorry.
First, I have to applaud you for, I know you guys are some of you are a little nervous up there. Trust me, it doesn't get any easier. But I really want to applaud you for this. And I guess I'd just ask, is this a project that you guys worked at with the University of Mass? Obviously you go there. Is it something your engineering schools ask you to do and to get together as a group to do this? And obviously it seems like it's spread a lot further than just the project.
We actually were one of the first participants in a new program that UMass Lowell has started, which is the Difference Maker program, and it's for entrepreneurs and anyone with ideas. Really is the main thing. Our school really wants us to see us succeed and be world ready, as they call it. So they're trying to facilitate ideas, get teams together, especially interdisciplinary. And so we went into that program. We learned a lot about business, as most of us are engineers. And from that, we actually won the campus-wide Difference Maker competition. So we got some funding from alumni to continue making our prototypes. And now we're actually forming a full company, a nonprofit, Nonspec.
I have a follow-up question to Jane. Obviously, very humbled today to see engineering students with such an amazing application of plastics, children, third world countries, prosthetic limb. What could IAPD and IAPD members do for you to further this along and encourage more young engineering students like you to experiment with plastics and help change the world?
That's a good question.
A good question. I know personally I come from a mechanical engineering background, and I'm going to be honest, none of my professors liked plastic. In fact, when I proposed a design out of plastic, the response was less than favorable. That's the charitable response I'm going to give to.
And I'm.
Let's not. Because
I'm going to explain that.
Yeah.
UMass Lowell actually has the only accredited plastics engineering program in the country. And it's a very small program, and not many people know about it. And just as any other engineering majors go head-to-head about what they know, plastics does that with mechanical a lot. But luckily, we're all friends. And so we combined the design aspect with the plastics knowledge that I had. And
yeah. And it was actually such an issue that all of our first-end prototypes are all made out of aluminum because my machinist refused to touch plastic at the time. We fixed that. He's over that now. He's much better with it. But just for my standing, I think being aware of the fact that there are material opportunities that are not just 60-61 every single time I'm doing a project. That's my stock for everything. Would be enormous for outreach in terms of getting plastic out there and getting people to use it. Because, I mean, this one converted me. I had no idea beforehand. But yeah.
So to answer your question, I don't know where my mic went. I would think having any opportunities for students to attend conferences or have talks from different companies within the IAPD realm is important, because having that knowledge, even just from a 30-minute session, going into industry, that knowledge comes back and you say, oh, I know about this, and I know where to go to get more information or to get products.
Okay. No, you may not.
Oh, no problem. Sorry.
Some very, very bright young men and women there, and I hope you all brought your resumes, because we are going to bombard you as soon as this session is over. And I love the slide that said plastics is the obvious choice. If we can get more people to understand that, we're going to be some very happy people in this room. Great job.